was looking at a website, and I figured I might be using this website. It's HTTPS, which means encrypted. What's the quality of their encryption? And so I ran a test against it. And instead of an A, which is what ours gets, it got an F. And so I wanted to see what was wrong with it, and that led to this. It has a particular vulnerability, and so I looked up about that vulnerability, and so here's what we find out about. It's based on a violation of a principle. And the principle was invented by this fellow called Moxie Marlinspike. I think that's an actual name. He calls it the Cryptographic Doom Principle. And it says, if you have to, having received an encrypted message, if you have to perform any cryptographic operation before you verify the message authentication code on the message, somehow, inevitably, it will lead to doom. That's the principle. You must arrange your cryptographic primitives so that the very first thing the recipient does is verify the MAC, the message authentication code. And that's a cryptographic digest, typically, based on a secret key that's shared between the sender and the receiver. And so the receiver can use that key on the little bit of message, which is known to be the identification code, can see if that code matches what you should get when you digest the rest of the message. And if it is, then you go ahead and decrypt or whatever else. That's how you're supposed to do it. So that's the proper use of the MAC, the message authentication code. So here's an example of how you're supposed to do it. The parties are Alice and Bob, A and B. Alice is sending a message to Bob. Alice has somehow encrypted it. Bob is supposed to decrypt it. And later we'll introduce M. That's Morgan. That's the man in the middle who's going to try to attack things. So Alice sends the following thing. Alice is interested in passing the message P. P is for plain text. And so what she does is she encrypts the plain text. And she appends to the end of it the authentication code, which is another encryption using a different key, of the encrypted plain text. And E of P includes, it's not just the encryption, it's everything you need to decrypt it. For example, an indication of what method I use to encrypt it. And if there's an initialization vector needed for decrypting, that's part of it as well. Right. So what Bob should do then is first verify this part. Because it's there, it's part of the message. Bob can look at that, can look at this, apply the MAC algorithm that is shared between them, see if they agree. If the MAC on this agrees with this, then the message is authentic. And if that's fine, then Bob will decrypt P. We'll go ahead and use whatever decryption method is appropriate for that, and ends up getting P. And what's good about this is it verifies the integrity of this. That's the whole purpose of the MAC, to verify integrity. While it's doing that, of course, it's also verifying the integrity of P. But it provides no information whatsoever about P. Partially because E pretty much hides anything about P. And secondly, the MAC, the cryptographic digest, also hides the contents of what's inside of it. And so that's the good stuff. Now, there are alternatives to that. That one has a name. It's called encrypt then authenticate, or encrypt then MAC, or ETA. That's what you're supposed to do. People have all sorts of abbreviations for it, and they all sound identical, but they're different. Here's a bad one: authenticate and encrypt, E and A. And it was originally used in the SSH protocols, although I don't think it is anymore. And so it looks very similar. Alice sends to P, to Bob this. Now, what's the difference? The difference is that the MAC is only covering P, and not E of P, not the encryption, but the plain text itself. And so what is poor Bob supposed to do? In order to verify, Bob can't do that first. So this violates this Doom principle. Bob has got to first decrypt this, getting P, and then confirm that that's right. So this will ultimately lead to doom. But how? Well, there's the good, the not good, and the bad. Good, it does verify the integrity of P, because after all, That's what it's supposed to do. However, it may theoretically reveal information about P if MAC is somehow reversible. Usually it isn't, and so we don't have to worry about that. But it doesn't actually check that this is unharmed. That's not so good, but what's really bad is that it turns out that, it means that I'm not going to go into, a man in the middle, that's Morton here, can try various versions of E of P, noting whether Bob actually gets as far as trying to verify this. Bob can't verify that part until having done the decryption. And by trying various versions of that and doing timing analysis, Morton can actually discover information about the message. I'm not going to go into the details. It turns out that there's another attack on SSH based again on the fact that it does more or less this, called a plain text recovery attack. MAC then encrypt. I said it sounds almost the same, but here's, this is, again, subtly different. What Alice does is take the plain text, append an authentication code to the plain text, and then encrypt the whole thing. Now this violates that Doom principle, because it's not the first thing that Bob can do to verify the MAC. Bob has to first decrypt that, deriving P in MAC, and then can confirm. So it's not the very first thing that Bob does. So the principle is violated. Where is the Doom? Well, again, good and not good and bad. It verifies the integrity of P. That's nice. It does not actually verify the integrity of the whole package, but it's vulnerable to an attack which I will show you in some detail. It was due to someone named Vodene, man-in-the-middle attack. It's also known as Lucky 13 for no obvious reason. In order to describe the attack, I've got to show you how decryption works in a particular set of cipher suites. When you're using a browser, your browser coordinates with the server, saying, these are the cipher suites that I'm willing to use. And the server says, well, here's my favorite set of cipher suites, typically by giving them an order. And they agree on the best one. And so this only will apply if the cipher suite that they choose is a cipher block chaining method. And the way that works is, here's the ciphertext, but it's divided into blocks. And for our purposes, let's imagine that a block is 32 bytes. There's going to be a key, which is private. It's shared, but it's private between Alice and Bob. Morton doesn't know it. And there's an initialization vector, which is sent along with the ciphertext. Anyone can see that. And there is a decryption method, which is done only on a block. Typically, the method is known as the AES method, but there are all sorts of alternatives. AES is the Advanced Encryption Standard, which was developed about 20 years ago. So one block of that is decrypted using the key, and then the result is bit by bit and exclusive OR to get the plain text for the first block. Then the second block, you imagine you do the same thing, but not quite. Instead of exclusive OR in the initialization vector, it exclusive ORs in the ciphertext of the previous block. That's just to make it more complicated. And that gives you the next block of plain text. And finally, this is a 3-block thing, and you get the third block of plain text again by using the ciphertext from the second block as part of the information. Now, if you're using a block method, what happens if your message is not an integral of 32 bytes long? What you do is you pad it. And the padding is going to be at least 1 byte because of the way it works, and I'll show you soon. But it can be up to, well, you imagine it could be almost an entire block worth. It could be padding. And the way that padding is done is it's in the plain text before it was encrypted. And so once this is all done, you expect that the very last byte here is a number, like 7. And if it's 7, that means there are 7 bytes of padding. and we expect to see a 7 in the last 7 blocks, 7 bytes. They should all say the same thing. They should all say 7. There's a check for that, and Bob has to do that check. It's called the padding check. And if it passes that, the next thing you do is you check for the MAC. Now the MAC is going to be here. Before the padding is at the very end. Right before that comes the MAC, and the MAC is 20 bytes long. It's a standard. At least for this talk, it's 20 bytes long. And so you can check that, and then the rest of it is the actual message. So there's message here, there's a MAC, and then there's padding. That's how it should look. Again, what was encrypted was the message and the MAC. I didn't show you, but there's padding at the end as well. And the padding has got to be done exactly the way I showed you. All right. And I got that right from Wikipedia. Right. So there's an attack, which is a specific attack in the category of a padding oracle attack. So the pad has got to be at least 1 byte long. That's the way it is. It's got to be at least 1. And what Bob is doing, as I mentioned, is decrypting, looking at the last byte. It sees maybe 7, verifies that the last 7 bytes all say 7. If not, it's a padding error. Otherwise, Bob can verify this. Now, if I can force, well, we'll get to the details in order here. Morton here, the bad guy, the man in the middle, is going to arbitrarily modify R. Now R is this byte right here. A man in the middle, you see, is standing between Alice and Bob. All the man in the middle can see is the ciphertext, but the man in the middle can modify it before sending it on. And so what Morton does is modify that 1 byte. Now what's the effect of that? The effect of that is that this plain text comes out completely gibberish. That's unfortunate, but no worries. The important thing is it modifies this. Now by trying all possible modifications of this, and it's only 1 byte long, 256 values, there's the original value, 255 other values, I can eventually, I'm Morton now, I can eventually try it until it turns out that this byte is a 1. And when that byte is a 1, Bob will say, oh, the padding is fine. And then Bob will continue, assuming that the next 20 bytes here are MAC, and we'll say, no, that's wrong. But by carefully timing how long it took, M can discover whether that was a 1 or not. Because if the padding check fails, Bob isn't even going to try the MAC check. And so if it happened very quickly, it was a padding error. If it doesn't happen quickly, it was an MAC error, and therefore I know that this last byte turned this into a 1. Well, if I know that that turned it into a 1, I actually know what the last byte is here. The last byte here is the original thing here, XOR 1. I've now discovered 1 byte of the plain text. I know that this wasn't a 1, it was something else, and I know what it was. And then, once I know what that is, I can do the same trick on this and on this. I eventually can figure out the entire plain text. Now let's see if what I said here is that. Either Bob will get a padding error or a MAC error. Morton distinguishes them by timing. By trying at most 255 possible modifications of that particular byte R, Morton can eventually trigger a MAC error, not a padding error. And therefore, Morton has decrypted the last byte of the ciphertext. Last byte of the plain text, this should say. I'll fix it. The way I built this file, by the way, is by using Markdown and then Pandoc. I'll tell you all about it offline. So, Morton can now force that thing, can keep doing and get the entire plain text. All right. So how do you circumvent this attack? How do you fix this bug? It was a bug, and it was announced as a bug in the SSH, actually in the open SSH library, and they fixed it. And that is, you do everything in constant time. You make sure that you do all the padding check and you do the MAC check no matter what. If the padding check fails, you do the MAC check anyway. So there's no way of telling my time. But how long should you spend on the padding check, which depends on how much padding there is? Well, no, you pretend that the padding is the maximum padding. And you have a little mask saying, after this point, I'll pretend to do the check, but I'm not actually doing it. And the MAC is going to start at some location. But where is that location? Again, you can use masking to determine whether you actually use the result or not. So there's essentially one bit of result. Is it good or is it bad? And you keep handing into it as you find things might be bad. But you keep doing the calculations until you get to the end. So no matter what happens, you spent the same amount of time. That was the fix. They got it wrong. It fixed the bug and introduced a new one. And so, let me just, you never tell Morton which check has failed, and you don't give timing results either. Each test goes using an AND into the success variable, and you know how much padding there is, and so to ignore the non-padding bytes that you don't really have to check, you check them anyway, but you ignore the result. And they introduced this in the TLS, and in May 2016, it was reported by Yuri Somorovsky. He reported it to the open SSL community, and within half a month, it was fixed and reported to the wider community once the fix was known. It was a one-line fix. Now, you can actually test hosts using a website. You can also use SSL Labs, which is how I found the problem initially. And let me just show you here. I'll actually run it. I'm not going to go to the website. I have a little program written in Go. I didn't write it. But I just said make test. It tests our server, and it tests that one, the SOAS server. And so our server is not vulnerable. The SOAS server is vulnerable. I just tested them. So between last night and tonight, they haven't fixed it. Somehow I'm not surprised. I'll tell you if you're interested offline why I'm interested in this particular website. All right, so back to here. All right, so I'm going to give you some of the details, but maybe I won't be able to show you all of it, because the truth to tell, I don't understand it completely myself. The description I found, there's only one careful description, and it's murky. But we'll try.
Sorry, but I know that you said, and explained on the previous slide, that this fixes.
Yes.
Yeah, but they fixed one problem, introduced another.
That's right.
So now you will tell us about this other problem.
Exactly.
Okay.
The problem that they failed to fix. Exactly. So, again, Alice is using this not very good method, sending this. Now, I've been a bit more careful here. But what she really sends is the plain text, followed by the MAC, which is 20 bytes, followed by the padding, and finally the padding length in the very last byte. That's what I said before. And in this CBC mode. And Bob first has to decrypt it, then verifies the padding by looking at the padding length and making sure that all of the padding has the same value, and then verifies the MAC, and then accepts P if everything's good. And it's violating the cryptographic Doom Principle. But it should be fine now because everything's constant time. Now, the coding error was that the constant time code did not check for a valid padding length. And if you send it a padding length bigger than the maximum possible, you can play tricks. I'll show you some detail of that. The fix was a one-liner. And into the bit that you're going to say is good or bad, whether or not the padding length is valid. And if it's invalid, you still do all the work, but you know that the result is invalid now. And so the coding error was that B's mask, the mask that was used to determine which bytes are worth checking for the padding, can be fooled to check no bytes of padding at all. And so it doesn't do the padding check. It goes right onto the map check. You have a question, Jim?
Well, I thought what you just said was that if you send it a padding length that exceeds the maximum.
Yes.
It's an oxymoron, isn't it? Because if you define the maximum.
Well, they didn't check for that, and I'll show you. It failed to check for it. The fix is now to check for that. So it's a one-line fix to the fix. But, okay. It turns out that M can discover if a message, if a plain text is made entirely of bytes with a value having greater than the max pad plus 20. 20 is the length of the MAC. Here's a little bit of detail. But read the last line first. Sorry, but the details are pretty murky. As I said, I didn't completely understand it, but this is what I did understand. Again, we're going to assume the block length is 32 bytes. The MAC length is 20. The padding length, a proper padding length, is constrained. It's got to be at least 1, and it can't be bigger than the block length minus that 1 byte at the end minus the 20 for the MAC. And that turns out to be 11 bytes. So the maximum reasonable value is 11. Well, what if you set it to 31? You just make sure that somehow you set the plain text. Now, how you do that is an interesting question, but if you can send something whose plain text at the very end has a 31, then that means that unless it's checked for, which it wasn't being checked for, that Bob is going to start doing the check for the pad all the way off the 32 bytes. We'll mask it as saying it's not important, but it's going to then check unimportant stuff. A lot of constant time work that is going to say it's fine. So in fact, Bob has not done any padding check. In fact, what happens is that the MAC isn't checked either, because the MAC happens after the padding. And if you think that the padding is the entire block, you're not going to check, then the MAC is well off the block, and the mask will say, we'll check it, but don't do anything about the result. And therefore, the MAC never gets checked. And so, by looking again at timing, M can discover if a message is made entirely of bytes which have a bad value. Now, this is the part I'm not so sure about. If M can post to B in an unauthenticated way, that is, B accepts both HTTPS and HTTP, M can invoke the padding and MAC check on plain text that it has chosen, not ciphertext, which it can't build, but plain text, which it can build. I don't know quite how this works. And then, what M does is align an unknown byte, R, where at the start of 2 blocks containing 31 that it posts to B. Okay, so it's going back to here. It's at this block. By trying various things there, it can affect what's there. And let's see. And when the MAC check passes, then the target byte is that. And it turns out that by some care, you can get 16 bytes of plain text. And that's enough to be able to read cookies, apparently. So the fix, there's a blog from which I read most of this. Under TLS 1.1, if the connection is using the AES CBC method, and if B supports AES-NI. NI is new instructions. Intel and AMD chips now have instructions for doing AES in the hardware. And it was in that routine that called the hardware that this error was. Then M can recover at least 16 bytes of anything it can get the client to repeatedly send, that is, get Alice to send repeatedly, usually by adding some JavaScript that does that, just before M-control data. Apparently, this is actually possible. The public report happened about a half month after the first report. The fix was developed by Kurt Ricks, and it was a one-liner. B should add a constant time check that P is in fact valid. And now for something completely different. I have a little bit of time. I want to share something completely different.
Can I ask you a question?
Yes.
I don't know much about it, but it occurs to me if it's all based on timing, rather than keep it constant, cannot we simply make random?
Yeah, that would be another approach to randomize the time that you spend doing something. I guess why that wasn't usually taken is because that will generally slow collect connections down, because you have to make the randomness over a fairly wide range. And maybe that was why people chose not to do that. I think that would work. I want to show you this particular website. Actually, it's already up here. https map.what3words.com/lunch.hops.liked. And what it is right there, where we are at the moment. Here's the Marksbury building.
That sounds like Egypt.
Well, right. Well, let's change the last word. Give me a word in English.
Race car.
Well, let's just say car. It might have race car. Right, where is that? That is, I have no idea where that is. Let's see if I can. You can tell immediately it's in New Jersey, huh? It's in the middle of a city. Very good. There's a lake there. What lake is it? Is this the New York area? Yeah, that looks like Manhattan. I don't know. Apparently, I can't read that. But anyway, it's there, it's somewhere in the map. What these folks at What3Words have done is they've divided the world into 3 by 3 meter regions, and each one has a name. And the names are 3 words. And you can identify a place by 3 words, which is kind of neat. I don't know what they do about the fact that the globe is round and it's not flat, but maybe they use a Mercator projection. I don't know. Things aren't so important up in the poles. And they also use shorter words for inhabited regions and longer words that you don't have to remember so easily for the less inhabited regions. And so back then to this. Every square is such an address. The address is in English, or any of about 20 languages, including Dutch and Arabic. And populated areas use shorter words, and it's useful for giving a precise location. That gave you the location right here, as opposed to where you're sitting, which would have a different 3-word thing. And it's all based, and there are apps which I just downloaded today for the Android and for iOS, so you can tell exactly where you are. It's connected to Google Maps if you want, so you can get from here to there by just giving these 3-letter things. You want to tell your friend where you live? Here are the 3 words. Yeah, we'll do it.
The typo can really set this wrong completely.
That's right. A typo will certainly make a mistake. And here's the original idea. It comes from XKCD. And the idea is how to make a good password. And the answer is don't do something silly like Troubadour 3, because it only has about 28 bits of entropy. It's difficult to get. It's easy to guess because it's only got 28 bits of entropy. It'll take about 3 days at 1,000 guesses a second. And it's also hard to remember. Was it trombone? No, it was troubadour. And one of the O's was a 0. Which one? And there was some symbol. What was the symbol? So it's hard to remember. On the other hand, the fellow who writes XKCD, what's his name?
Randall Monroe.
Yeah, Randall Monroe, thank you. He suggests you should make passwords that look like this. 4 words, randomly picked, like correct horse, battery stable. Easy to remember. You make some mnemonic. That's a battery stable, correct. All right? And it's got about 44 bits of entropy by his measure, and it'll take 550 years to guess. And so that was the basis then for this What3Words website. And I think that's kind of neat. So that's the point of keeping current, to see new stuff and neat stuff. So come again next week, you'll see some more new stuff and neat stuff. See you then.
So my password is correct. Cow, but
Cow battery staple is another good one. Why not? 3 words are most likely enough. We can find out where cow battery staple is, by the way. Let's just see if there is such a place. Gotta be 3 words, so let's try.
So we'll test the
Cow battery staple. I have no idea how they do the mapping. I've got a guess, but I don't know. The cow battery staple exists. Here it is, right in the middle of some building in a populated area.
Can I go the other way? Can I select any of these?
Yes, you can select a place, and then it'll tell you what its three-word thing is. So cow battery staple is in the middle of, there's a river.
Not the same spot.
It's not the same spot. Oh, that's word client space. I didn't do that right. Hold on. I didn't click the right thing here. Cow battery staple. Cow battery staple. Enter. Oh, that's why I didn't work maybe. I spelled things right. Cow battery staple. And let's say go. See if this actually works. All right. Now it's still giving me word client face. I have no idea why. It might not exist. Yeah, not all 3 possible words are going to exist. So that gets you somewhere on the move. All right. Time's up. See you next week.
That will make sense.